In this video, we'll review precedence of logical operators and propositional equivalences. Now, just as you may be familiar from working with arithmetic operators, logical operators also have precedence. And in particular, they have the following precedence. First would be negation of the strongest precedence, then and, then or, exclusive or, and implication, and then the biconditional, which is if and only if. It is probably best practice to avoid any ambiguity to use parentheses rather than relying on knowledge of precedence. Okay, let's just look at an example now, actually two examples where we can see precedence. So with precedence, we know that and has a stronger precedence than implication. So this with parentheses would be P and Q implies R. Now, I put the parentheses even though that is how the precedence would work, but I just want to show that this is not equivalent to P and Q implies R. And you can see that it has a different meaning based on where the parentheses are placed. And in the latter example, the parentheses are necessary because the precedence would make the P and Q have higher precedence than the implication, but these are not equivalent. And you can verify this completely as an exercise, but just to help with that, I just want to point out to consider what happens when P is false and say R is also false, but it really doesn't matter at that point. Once you have P is false, it's enough, because when P is false, we know that this entire proposition is false. However, here, when P is false, we know that the conjunction of P and Q is false, and false, regardless of what R is going to be a true implication. So this is just one example. So if P is false, we can see that these two propositions are not equivalent. Now, another example is P or Q and R. Now, because and has a greater precedence than or, this should be parenthesized this way if we mean the intention of just using the precedence. And we can see that this is not equivalent to P or Q and R. And one way that you can see this is that if, in this case, R is false and P is true. So if R is false, we know that this entire proposition is going to be false. However, here, if R is false, we know that this will be false. The conjunction of Q and R will be false, but because P is true in this case, so we know that P is true, and because of that, we know that this entire proposition will be true. So you can verify this completely with the truth table, but it's sufficient to show what I've done with just showing that with particular assignments to some of the variables that these would not be equivalent. And I didn't specify what the value of Q would need to be because what I had shown is sufficient, but you can verify this further using a truth table. Now, I also want to discuss propositional equivalences because implicitly I was using some of those when I was just deducing what P or R had to be in order to show that those propositional equivalences did not hold there. So now, how can you show that propositions are not equivalent? Now, in order to show that propositions are not equivalent, you can do two things. So you can do the entire truth table and show that the values for the propositions are not the same. And I was implicitly doing that in the previous example when I gave specific values for P or R that showed that they did not have the same truth assignment. Or you can give a counterexample. So now we want to try this again, and we want to show that these two propositions are not the same. And here we absolutely need to use the parentheses in order to specify, because we have the compound propositions composed of implications. So we have P implies Q implies R, or P implies Q implies R. So we want to show that these two propositions are not equivalent, and you can see this by using the truth tables or giving a counterexample. And a counterexample would be specific propositions P, Q, and R such that one implication is true and the other is false at the same time. So let's look at this now. And when we're designing and deciding which propositions we should have, in some respects we're considering the truth table, because if we look at this, we can see that, well, if P is false, if I have a proposition where P is false, then I know that this entire implication will be true. And then if I also have here P is false, then I know this entire implication will be true. So if I make R false, then I know that my right-hand side implication would be true, and my left-hand side implication would be false. So now I want to consider specific propositions, and it doesn't really matter what Q is, but for this example we are going to try to come up with propositions such that P is false, Q is false, and R is false. Doesn't really matter. Q doesn't really affect the truth assignment that I had just mentioned. But in particular, if our propositions are 7 is even, 3 is even, and 5 is even, we can see that these two propositions would not be equivalent. So let's just trace through this again now. So I'm just going to label this one 1 and this one 2. So first let's consider 1. P implies Q implies R. Okay, 7 is even is false, because we know that 7 is odd, so that's false, and we know 3 is even is false. So we have false implies false. We know that from the truth table for an implication that false implies false means the overall implication there is true. And then we have to evaluate true implies R. Well, we know R's 5 is even, which is false. True implies false for an implication, and this is the only time an implication is false. So we know that the first implication, 1, that we labeled 1, is false. Now let's look at the second one. We have P implies Q implies R. Now we have 7 is even, we know this is false. We can stop right now, and the reason why we can stop right now is because the second that we have an implication for which the premise is false, we know the entire implication is true. And I'm just filling this in here that, well, false, so here we know that once we know that the premise is false, that this entire implication is true. So we just gave an example of how we can show that two propositions are not equivalent by giving specific counter example. And as an exercise, you can also verify this by showing that these would not have the same truth tables. Now, I also wanted to take a moment just to discuss more useful propositional equivalences that you may use. So one is the contrapositive. Now, if you have an implication P implies Q, it's logically equivalent to its contrapositive, which is not Q implies not P. So basically, if we negate the conclusion, then we negate the premise. A tautology is a statement that is always true. So if we have a proposition P, either P is true or its negation is true. So when we take that disjunction of P or its negation, that must always be true. So that's a tautology. Similarly, we know that either P is true or its negation is true. So when we take the conjunction of P and its negation, we know that that must be false. So that's a contradiction. With idempotent, that's when we're taking the disjunction or the conjunction of a proposition with itself, and in that case, it's just going to be equivalent to the proposition. Now, we've already discussed this, but an implication is also equivalent to the negation of the premise or the conclusion. So P implies Q is also equivalent to not P or Q. And identity, so if we have P and it is in a conjunction with something that's true, well, we know that that conjunction will just be equivalent to whatever P is. And similarly, if we have a disjunction of P and something that's false, then that disjunction will be equivalent to P. Finally, for domination, if we are taking the disjunction of a proposition in true, so P or true, we know that that is equivalent to true. And if we are taking the conjunction of a proposition with false, P and false, then we know that that entire conjunction must be false. Now, for double negation, when we negate the negation of a proposition, we just get the original proposition. And when we have disjunction or conjunction, so P or Q is equivalent to Q or P, and P and Q is equivalent to Q and P. That just means the order in which we have the propositions in the disjunction or the conjunction doesn't matter. Now, disjunction and conjunction is also associative, and all that means is that it doesn't matter how we group the conjunction or the disjunction. So if we take P or Q and we take that disjunction and then we do the or with R, it's equivalent to first doing the disjunction between Q and R and then doing or with P. Similarly, if we first consider P and Q and then take the conjunction of that with R, it's equivalent to first taking the conjunction of Q and R and then taking the conjunction with P. And the important thing is you'll notice is that associativity only applies when it's the same operator, so it's all conjunctions or it's all disjunctions. So I just want to mention that that's very important. But you'll notice that when you have different operations combined, when you have conjunction and disjunction, that is when the distributive law applies. So in the distributive law, we are essentially distributing the opposite operator. So for P and Q or R, that's equivalent to taking the conjunction with P and Q and oring that with the conjunction of P and R. Similarly, if we want to have P or Q and R, we can first take the disjunction of P and Q, so that's P or Q, and then take the conjunction with P or R. That's the distributive law. Now, De Morgan's law is when we want to negate a conjunction or disjunction. So not P and Q is equivalent to not P or not Q. And then not P or Q is equivalent to not P and not Q. Now the biconditional, a nice way to remember it, especially as truth table, is to recall that P if and only if Q is equivalent to both implications, P implies Q and Q implies P. So that is what that equivalence is. So that P if and only if Q, that's the double arrow, is equivalent to P implies Q and Q implies P. And finally, the exclusive or of P and Q is equivalent to P if and only if not Q. Now, all of these equivalences you can actually verify using truth tables. And that might be good practice if you're not feeling confident about any of these, that just draw the truth tables and verify them to make sure that you believe that they actually are equivalences. Now let's just do a practice problem. Okay, so now I have equivalence with. Okay, let's start. So we are going to just start with the exclusive OR. So we have the exclusive OR of P and Q. And we just showed the equivalence that the exclusive OR of P and Q is equivalent to P if and only if not Q. So that's the equivalence with the exclusive OR. Now, we can use the equivalence of the biconditional. And what I mean by that is we can take this if and only if, so P if and only if not Q, and we can write this as P implies not Q, and not Q implies P. So what I had just used is the equivalence with the biconditional. Now, I can rewrite the two implications in terms of the equivalence of an implication. So recall that P implies Q is equivalent to not P or Q. So I'm going to negate P, or in this case P implies not Q, so it's not P, or not Q. And here I have to negate the premise, but the premise is not Q. So when I negate that, it's a double negation. So I'm going to get Q, and I take the disjunction with the conclusion, so it's P. So Q or P. So this is using implication equivalence and double negation. Okay, so now I have disjunction and conjunction. So I want to demonstrate what the distributive law looks like in this case. So the way that we can think of this is that we can distribute the not P across the conjunction with the Q or P. So in order to do that, the first thing I'll do is I'll say, well, the first will be, the new clause will be not P and Q. And then I will use the or, and I will take the conjunction again of not P and P. And now I will do another disjunction, because now I will take not Q and the conjunction with Q or P. So this will give me not Q and Q, or not Q and P. And what I just applied there was the distributive law, twice actually. Okay, so now if we look at this, we have not P and not Q and Q. And remember that those are contradictions. So let's just write that. So we have not P and Q, or false, or false. And what I was just doing when I replaced not P and P with false and not Q and Q with false is I was observing that I have a contradiction. So then I have not Q and P. So that's a contradiction where I replaced not P and not Q and Q. Those are contradictions because a proposition and its negation cannot both be true simultaneously. And now I have to use the identity. So when I use the identity, and I'm just going to also use the commutativity also at the same time. So what I mean by identity is that when you have or and false, you can basically remove the false from the disjunction because it's going to be whatever else is the disjunction. And then by using the commutative law, I can get this in the exact same format as the equivalence above. So then we have not Q I actually need to flip the not Q. So I'm using the commutative law in two places. So first, I'm using the commutative law when I move this to the front. So I can move that to be the first term of the disjunction, but I'm also within that conjunction, I'm going to flip those using a commutative law. So I'm going to have P and not Q, and then I have the disjunction. And now I'm going to use the commutative law in this term now when I move it. It's going to be Q and not P. And now we have shown that the exclusive or of P and Q is equivalent to P and not Q or Q and not P.